For thousands of years, humans looked up at the sky with a mixture of wonder and frustration. Birds moved effortlessly through the air, rising, gliding, and disappearing into the clouds, while humans remained firmly bound to the ground. The sky felt distant and unreachable, almost forbidden, as if it belonged to another world entirely. Yet despite fear, limits, and repeated failures, one simple question never left the human mind. Could humans ever fly? That question refused to fade, passing from one generation to the next, quietly shaping the future of human progress. In ancient times, flight existed only in imagination. Myths and legends were filled with winged gods, flying heroes, and magical journeys through the sky. These stories reflected humanity's deep desire to escape gravity, but they offered no real understanding of how flight could actually work. There was no science, no engineering, only belief and fantasy. Many people assumed the sky was not meant for humans, that flying was reserved for gods and birds alone, and that any human attempt to reach it was doomed to fail. The first serious attempt to challenge this belief came in the 9th century with Abbas ibn Firnas. Determined to test whether humans could truly fly, he constructed wings from wood and cloth, inspired by the structure of birds. Standing at a high point, he leapt into the air. For a few brief seconds, he remained airborne, something no human had achieved before. The landing ended in a crash, leaving him injured, but his attempt proved a critical point. Flight was not impossible. It could be attempted, studied, and improved. His failure became a foundation, not an end. Birds are not merely living creatures that happen to fly. They are highly refined, perfectly optimized flying machines shaped by millions of years of natural selection, where every detail of their bodies serves a clear aerodynamic purpose. Their wide wings provide a large surface area that allows them to generate lift efficiently. Their lightweight skeletal structures reduce the force needed to stay airborne, and their smooth, streamlined shapes minimize air resistance as they move through the sky. Nothing in a bird's design is accidental, from the curvature of its wings to the positioning of its feathers, all of which work together to control airflow, manage pressure differences, and maintain stability during flight. When humans began to seriously study flight, they quickly understood that if sustained, controlled flight was even possible, nature must have already discovered the most efficient solution long before human engineering existed. This realization shifted the approach of early engineers and scientists, who stopped treating birds as objects to imitate visually and instead began analyzing them as natural examples of aerodynamic efficiency. By observing how birds interact with air rather than simply how they look, engineers learned to identify the underlying physical principles governing lift, drag, balance, and energy efficiency, allowing them to translate nature's solutions into mechanical designs that obey the same laws of physics and ultimately make human flight possible. The most important force in all forms of flight is lift, because without lift, no object, whether natural or mechanical, can ever leave the ground or remain suspended in the air for more than a brief moment. Lift is the upward force created when a moving object interacts with air in a controlled and purposeful way, and it forms the very foundation of flight for birds, aircraft, and every flying machine ever built. When a bird spreads its wings, those wings are not held flat by chance. Their curved shape and carefully adjusted angle force air to behave differently above and below the wing. Air traveling over the upper surface is accelerated and stretched over a longer path, while the air beneath the wing moves more slowly and is slightly compressed. This difference in airspeed creates a pressure imbalance that is essential for flight. According to the fundamental laws of physics, faster-moving air produces lower pressure, while slower-moving air produces higher pressure, resulting in low pressure above the wing and high pressure below it. The higher pressure underneath the wing pushes upward against the lower pressure above, generating a lifting force that raises the bird into the air and keeps it there as long as sufficient airflow is maintained. This same mechanism explains why birds can glide, soar, and maneuver with such efficiency. Airplane wings are designed to take advantage of exactly this principle, using a curved upper surface and a flatter lower surface to manage airflow in the same controlled manner. Engineers do not rely on imitation or guesswork. They rely on the certainty that lift obeys universal physical laws that do not change based on size, material, or the nature of the flying object. Lift cannot be explained by Bernoulli's principle alone, because flight is the result of multiple physical laws working together rather than a single effect. According to Newton's third law of motion, for every action there is an equal and opposite reaction, and this law plays a crucial role in how wings generate lift. When a wing moves through the air, it does not simply allow air to pass over and under it. It actively pushes air downward. This downward deflection of air is an action, and in response to that action, the air exerts an equal and opposite force upward on the wing. That upward reaction force contributes directly to lift and helps keep the flying object in the air. Birds use this principle clearly when they flap their wings, forcefully pushing air downward with each stroke, which results in an upward lift that supports their weight. Airplanes achieve the same physical effect in a different way, not by flapping, but by moving forward at high speed so that their wings continuously redirect air downward as it flows past them. Although the mechanisms appear different, flapping wings versus fixed wings moving through air, the underlying physics is identical, demonstrating that lift is produced through a combination of pressure differences and action, reaction forces governed by the same unchanging laws of motion. Flight is not only about generating enough lift to stay in the air, but also about maintaining stability and control while moving through constantly changing air conditions. A flying object must be able to balance itself and adjust its orientation in all directions. Otherwise, even a small disturbance could cause a loss of control. Birds achieve this stability by using different parts of their bodies for specific types of motion. Their wings manage roll by adjusting lift on either side, while their tails act as stabilizers that help control balance and direction. Airplanes apply the same logic using engineered control surfaces based on the same physical principles. The wings control roll by changing lift from side to side. Horizontal stabilizers control pitch by managing up and down rotation, and vertical stabilizers control yaw by keeping the aircraft aligned with its direction of travel. This system is based on rotational physics, which deals with motion around different axes and the forces and moments that influence that motion. By following bird-inspired aerodynamic designs and applying these rotational principles, airplanes are able to remain stable, responsive, and controllable even in turbulent air, ensuring safe and predictable flight under a wide range of conditions. Humans did not design airplanes to resemble birds for aesthetic or artistic reasons, but because birds already operate in perfect harmony with the laws of aerodynamics. The physics that allows a bird to fly is not unique to living creatures. It is universal and applies equally to any object moving through air. Physics does not change based on species, size, or material, which means the same rules that govern a bird's wings also govern the wings of an aircraft. Over millions of years, nature has refined bird anatomy into one of the most efficient flight systems possible, solving complex problems such as lift generation, drag reduction, stability, and energy efficiency long before humans understood the science behind them. When engineers studied birds, they did not attempt to replicate feathers or flapping wings exactly. Instead, they translated nature's solutions into mechanical forms that obey the same physical principles. As a result, airplanes are not direct copies of birds, but carefully engineered interpretations of the same aerodynamic laws. This is why, when science followed nature rather than imagination, human flight became possible, because in the end it is physics that explains why birds can fly and why airplanes, by necessity, must share the same fundamental shape and design logic.